Hi, we're ME482 Group 18, and this is Product Analysis and Redesign of a Food Processor. Food processors are appliances that crush, grind, chop, and shred food using a blade and attachments driven by an electric motor. Food processors reduce the labor involved in mixing food ingredients and chopping them. Food processors are produced in about 1 million units a year, and the manufacturing of them brings in around $544 million of annual revenue in the US. The total food processing and blender industry revenue increased 4.5% from 2018 to 2023, and is projected to increase 1.4% from 2023 to 2028. So although it's slowing down, it's still a fast-growing industry. Primary customers who'd use the product are people who enjoy cooking meals at home, as well as health-cautious individuals. These people usually make meals that involve fruits, vegetables, and even sauces, for which a food processor like this is useful to have on hand in the kitchen. Secondary customers include food trucks as well as smaller family-owned restaurants.
Here is an exploded view of our chosen product. Our product consists of a total of 29 components, excluding fasteners. It should be noted that the fasteners are not included in the exploded view for simplicity. Here is the FAST diagram for a food processor, which is the description of the functional requirements that it must fulfill. The food processor has one main functive branch, which is to mix ingredients. It does this by containing and destroying ingredients concurrently.
This is our first assembly sequence. It's a more bottom-up assembly sequence. So we're going to start out with the base plate, adding the rubber feet, the gear assembly, and the gear mounting plate. The gears are essentially closed off and covered from being exposed. Then we're going to move on to the motor and the cover for that. And then we're going to have the electrical housing. This essentially is all the electronic parts that control the motor and the switch. Then we're going to top it off finally with the bowl, the blade assembly, and then the bowl cover. Our second assembly sequence takes a little bit of a different approach. Instead of doing a bottom-up assembly, we kind of prioritize more sub-assemblies. So we're going to start with the motor, and then the gear mounting plate and the gear assembly. We're going to then move on to the electrical housing, as this is all connected to the motor. Then we're going to move on to the base plate, and then we're going to have the blade assembly, the bowl, and then the bowl cover after that. Comparing the two assembly sequences, we can see that they're fairly similar, but assembly sequence 2 ends up being a little bit better, mainly due to the fact that we're able to assemble it in parallel a lot easier.
Shown below is a function component mapping matrix for the food processor, which shows which components perform which functions. This shows which components are the most important, and therefore should be looked at first for redesign. As one can see, the food bowl, top blade, bottom blade, the food pusher, and the chute lock, as well as the food chute insert, perform the most functions.
So for our BOM and cost estimation, we're looking at roughly 22 unique and separate parts in our food processor. To estimate material costs, we used data that showed there is roughly $200 million in sales in a given year for food processors. Scaling that down to 2 million units for a given year and plugging it into the hub.com/manufacturing site provides us with the costs shown below. And then we also estimated the assembly time and assembly costs from there, providing us with the total cost of $26.11.
The quad chart is a tool used to classify the components based on their functional importance and manufacturing cost. Components with low functional importance are subject to elimination. Components with high functional importance and low manufacturing cost should be kept as is. However, components with high manufacturing cost and high functional importance are subject to be redesigned using design for manufacturing techniques.
We then constructed an FDT based on the needs of home cooks, food trucks, and restaurants. Many functions will stay the same, however, the speed needs to be increased for the trucks and restaurants who have to serve customers quickly. Using this information, we made a CCT. All of the components in the speed column of the FCMM from earlier will be considered modules. Changing the blade assembly seems to be the most effective and should increase the speed while keeping the redesign costs lower compared to changing the motor, for example. An example module is the blade assembly with the existing design shown on the left. It has 2 independent blades that attach on a shaft. To help speed the process of chopping the food, our new blade assembly on the right has 2 more blades, which are added on the opposite sides of each blade piece. They are also slightly thicker to resist wearing down easily. This change doesn't add any new components that need to be manufactured, and the geometry of the change is just a mirror of what already exists.
Within the food processor product family, the common interface consists of the circlip, which is the food processor body, as well as the switch plates and the rubber feet that keep it in place. However, as discussed previously, the blade sets can be changed out to vary the cutting speed. The switch positions, food bowl sizes, and the motor size and power can also be switched out for different price ranges and capacities of food processors.
The three main components in the manufacturing process in which there is variation come with the motor, the food bowl size, and the blade assembly. These three components combined end up creating roughly 12 different variants of the food processor, which can be manufactured.